morning friends. In this chapter 15 waves, up to the 15.12 numerical of exercise we discuss. Today we are going to discuss about the remaining numerical of exercise. Now the numerical number 15.13 of exercise given below the sum function of x and t represents the displacement of an elastic wave. State which of these represent first a traveling wave, second a stationary wave, or third none at all. Here the four equations of displacement of a wave in elastic medium are given. We have to represent, or we have to state that this displacement result represent which type of the wave, either the stationary wave or the traveling wave, or this displacement can't represent any type of wave. For that purpose, first is given y is equal to 2 cos 3x sine 10t. Right? Okay. There is a stationary wave. Why? Because there is the product of the two harmonic functions. So first we write like this way: a is equal to y is equal to 2 cos 3x into sine 10t. It represents a stationary wave. Because it is a product of two harmonic functions. One is in terms of cos 3x, that means in terms of position, and second is in terms of time t. So it is represented stationary wave. It is a product of the two harmonic wave. One in terms of position x, and other in terms of time t. Therefore, it is a stationary wave. Or in other words, that is in form of the given equation is similar form of the stationary wave y is equal to 2a sine kx into cos omega t. Right? Therefore, that is a stationary wave. Now the second equation, y is equal to under root of 2 minus xt. Okay, now it does not represent any elastic wave because here no terms involves of the harmonic function. Right? Again, it does not involve any harmonic function. Therefore, it does not represent any elastic wave. Right? So it is not, or it does not involve any harmonic function. So it cannot represent, so it cannot represent any elastic wave. Now in this equation of the displacement y is equal to under root of 2 minus xt. Here the sine or the cosine term is not present. Therefore, the displacement of particle at position x and time t is not varying with time. Therefore, it does not represent any harmonic function or any harmonic wave. So it does not involve any harmonic function. So it cannot represent any elastic wave. Now, third, C is equal to, the C is given as y is equal to 3 sine 0.5x minus 0.5t. and plus 4 cos phi x minus 0.5d. Here is our equation. Again we check it. Y is equal to 3 sin phi x minus 0.5d plus 4 cos phi x minus 0.5d. Now in this equation, these two terms are same. And you consider as a theta. So taking phi x minus 0.5t as theta. Therefore, our equation becomes y is equal to 3 sin theta plus 4 cos theta. 4 cos theta. Right? So this equation is similar to the y is equal to a sin theta plus phi. Y is equal to a sin theta plus phi. Right? Now y is equal to a sin theta plus phi. What is the simplification of this? Sin theta cos phi plus cos theta sin phi. Therefore, if taken common, sin theta cos phi plus cos theta sin phi. Right? So we can write like to get from a sin theta cos phi, or the a cos phi sin theta plus a sin phi cos theta. That is our equation number 2. That is our equation number 1. Compare equation 1 and 2. Compare equation 1 and 2. So a cos phi is equal to 3 because the sin theta is present. Now a sin phi is equal to 4 into cos theta. Right? Therefore, I can write a cos phi is equal to 3 and a sin phi is equal to 4. To find out the amplitude, so we can write like this way: a square cos square phi plus a square sin square phi is equal to a square taken common, cos square phi plus sin square phi is 1. Therefore, 3 square plus 4 square. Therefore, a square is equal to 25. Therefore, a is equal to 5 meter. So that is the amplitude of a wave represented by given equation. Again, so here by taking the phi x minus 0.5t as a theta, so equation becomes y is equal to 3 sin theta plus 4 cos theta. Now we are using this concept y is equal to a sin theta plus phi. Therefore, simplify this: a common, sin theta cos phi plus cos theta sin phi. Here our equation 1 is in terms of the theta. Therefore, a cos phi combined sin theta is in multiplication plus a sin phi into cos theta. Now compare this equation with 1. Left hand side are same, y. Therefore, a cos phi is equal to 3 and a sin phi is equal to 4. To find the amplitude of a wave, we make the square and adding, or we make first squaring the both term and adding this. Therefore, a square cos square phi plus a square sin square phi is equal to 3 square plus 4 square. Here a square common, cos square phi plus sin square phi 1. Therefore, a square is equal to 25. Therefore, a is equal to 5 meter. And a sin phi upon a cos phi, there is the tan phi. Tan phi is equal to 4 by 3. Therefore, phi is equal to tan inverse 4 by 3. That is the initial phase. That is the initial phase. Thus, given equation represents traveling harmonic wave with amplitude A is equal to 5 meter and initial phase 10 inverse 4 by 3. Thus, given equation is traveling harmonic wave with amplitude A is equal to 5 meter and initial phase phi is equal to 10 inverse 4 by 3. So if this type of the equations are given, so first we have to find out the amplitude and then what is the phase of this. Yes, we find out the amplitude and initial phase, so we can say that there is a harmonic wave and also there is the propagating or the traveling harmonic wave. Now, D is given as y is equal to cos sin t, y is equal to cos x sin t plus cos 2x sin 2. Now, this equation represents the superposition of the two stationary waves, because the first term represents the cos x sin t, that is similar to the y is equal to 2a sin kx cos omega t. So first term represents the stationary wave, second term it also represents the stationary wave. Right? Therefore, this equation represents the stationary wave. It is the superposition of the two stationary waves. Right? And these stationary waves are y1 is equal to this and y2 is equal to this. It is a stationary wave. Now it represents the superposition of two stationary waves. Y1 is equal to cos x sin t and y2 is equal to cos 2x sin 2t. So here the first is the stationary wave, second does not represent any elastic wave, while the third is the traveling wave, and fourth is also a stationary wave that represents the superposition of the two stationary waves y1 and y2. Clear? Now next 14. Wire stays between the two rigid support vibrate in its fundamental mode with a frequency of the 45 Hz. Now here the fundamental frequency is given 45 Hz. Therefore F1 is equal to 45 Hz. The mass of the wire is 3.5 to 10 is to minus 2 kg. Mass M is equal to 3.5 into 10 is to minus 2 kg. And the linear mass density mu is given as the 4 into 10 is to minus 2 kg per meter. So that is the linear mass density, mass of the wire, and fundamental frequency of the mode of oscillations are given. So what is the speed of transverse wave? What is the speed of transverse wave on the string and tension in the string? We have to find out the speed and also the tension in a string. So we know that So fundamental frequency of the stationary wave of a stationary wave that is F1 is equal to V upon 2L. F1 is equal to V upon 2L. Here the length of a wire is not given, but mu is given, so we know that. But mu is equal to M upon L. Therefore, L is equal to M upon mu. Substitute here. So we obtain F1 is equal to V mu upon 2M. V mu upon 2M. Therefore, we require the V. Therefore, V is equal to 2F1M upon mu. V is equal to, that means the speed of a transverse wave on a string. V is equal to 2F1M upon mu. Therefore, V is equal to 2F145. M is given 3.5, 10 is to minus 2 upon mu 4 into 10 is to minus 2. Therefore, the speed of a transverse wave in a string is 78.75 meter per second. That is our first answer. Again, the fundamental frequency of the stationary wave F1 is equal to V upon 2L. But here the length of a steel wire is not given. Instead of the length, here the mass and linear mass density mu given. Therefore, mu is equal to M upon L. Therefore, L is equal to M upon mu. We substitute here. Therefore, F1 is equal to V upon 2M upon mu. Mu is in denominator of denominator, છેદના છેદ અંશમાં આવશે અને V into mu upon 2M. આથી V ને કરતા બનાવીએ તો V. Now we make the equation in terms of the V. V is equal to 2F1M upon mu. Clear? Therefore, V is equal to F1 is given the 45, M is given 3.5 into 10 is to minus 2, and mu is given 4 into 10 is to minus 2. Therefore, V is equal to 78.75 meter per second. Now, we have to find out the next is the tension in a string. We know that the wave speed of a transverse wave, V is equal to under root of T upon mu, making the square. Therefore, V square is equal to T upon mu. Therefore, T is equal to mu into V square. Now we substitute the value of mu and V. Therefore, V is 4 into 10 is to minus 2, 0.04. Now V is 78.75 whole square. Thus we obtain 248.1 Newton. That much tension is in a string. Again, the wire stands between the two edges support vibrate in its fundamental frequency of 45 Hz. F1 is given 45. Mass of the wire is 3.5 to 10 is to minus 2 kg, and linear mass density is given 4 into 10 is to minus 2 kg per meter. What is the speed of a transverse wave? For that purpose, the fundamental frequency of the stationary wave F1 is equal to V upon 2L. Here L is not given, but the linear mass density mu given, mu is equal to M upon L. Therefore, L is equal to M upon mu. Substitute here. Therefore, F1 is equal to V mu upon 2M. Therefore, the equation of V is equal to 2F1M upon mu. Now we substitute the value. V is equal to 2F145 M 3.5 into 10 is to minus 2 upon 4 into 10 is to minus 2. Thus we obtain the speed of a transverse wave on a string is 78.75 meter per second. Now the section B, the tension in the string. For that purpose, we know the equation of the speed of a transverse wave. V is equal to under root of T upon mu. Making the square on both sides, V square is equal to T upon mu. Therefore, T is equal to mu V square. Substitute the value of mu and V. So we obtain the tension is 248.1 Newton. So that is our second answer. Now next numerical. A steel rod 100 centimeter length is clamped at its middle. The fundamental frequency of the longitudinal vibration of the rod are given to be F1 is given as 2.53 kilohertz. That means the 2.53 into 10 is to 3 hertz. What is the speed of sound in steel wire? What is the speed of sound in steel wire? We know that the speed of a sound wave V is equal to frequency into wavelength. Frequency is given, we have to find out the wavelength. And also, here the frequency of the longitudinal vibration of the rod are given to be 2.53 kilohertz. And that is the fundamental frequency. Therefore, the rod is oscillate with the fundamental mode of oscillation. That means the N is equal to 1. For that purpose, we can write like this way. For a steel wire, wavelength of nth mode of oscillation, lambda n is equal to 2L upon n. Right? Here, n is equal to 1. Therefore, lambda 1 is equal to 2L. Is equal to wavelength of first harmonic. Wavelength of first harmonic. Now the speed of a sound wave in a steel. Speed of a sound wave in a steel rod is V is equal to F1 lambda 1. But from this equation, lambda 1 is equal to 2L. Therefore, speed of a sound wave 2F1L. 2F1L. Substitute the value to F1. 2.53 into 10 is to 3. Now length of a steel rod is given 100 centimeter. That means the 1 meter. So that is 1. Therefore, the speed of a sound wave in a steel rod is 5060 meter per second. Very easy numerical, that is important for the new competitive exam. Again, the steel rod of length 200 centimeter length is clamped at its middle. The fundamental frequency of longitudinal vibration of the rod are given as 2.53 kilohertz. So what is the speed of sound in steel? Now we know that the wavelength of a sound wave in steel wire with nth mode of oscillation, lambda n is equal to 2L upon n. Here n is equal to 1. Therefore, lambda 1 is equal to 2L is the wavelength of first harmonic. Now the speed of a sound wave in steel rod, V is equal to F1 lambda 1. But lambda 1 just we obtained, that is the 2L. Therefore, V is equal to 2F1L. So 2F1 is 2.53 into 10 is to 3, and length L is equal to 100 centimeter. That means the 1 meter. So the speed of a sound wave in steel wire is 5060. That means the 5060 meter per second. Clear this? Okay. Now the next numerical we discuss.